Hello, so today we are doing this problem called cheapest flights within K-stops. And the problem says we have n cities that are connected by m flights, and each flight starts from one city, U, and then arrives at V, and the price is W. And given all cities and flights, together with starting city, source, and destination, our task is to find the cheapest price from source to destination with up to K stops. And if there is no such route, we can just return -1. So this is the problem we have. And the size of the flights will, I think this information, yeah, so basically the format of each flight will be source, destination, and price. That's what we see here. And some limits for the numbers. N is between 1 and 100, and there will not be any duplicate flights or self cycles. So that's guaranteed. And so, for example, if we take this one, we get that we start at 0 and we want to go to 2. We can either go from 0 directly to 2, and that's 500. And also it says that within K stops, so we can only make one stop, we cannot make more. We can also go from 0 to 2 via 1, which is just one stop, counts as just one stop, so 200, and so the minimum is 200. For this example, we want to go from 0 to 2, but within 0 stops. So up to K stops, so the max we can go to is K stops. So here 0 stops, so we can't go any stop in between. So even though here we can go from 0 to 1 and then to 2 with 200, which is smaller than 500, we can't do that because of the other constraint that K has to be equal to 0, and through 1 it will be equal to 1. So those are the constraints that we have. So let's see how we can solve this problem. So this so we are looking for the minimum cost, right? So minimum cost. So essentially what we are looking for is shortest path in terms of cost. Not just in terms of the number of edges, right? And so whenever we have this on a graph, we can think of BFS. But we just have to be careful here, because BFS usually, the shortest path is for edges that are n-weighted, but here our edges have a weight, which is their cycle, the cost, right? And we have also the extra constraint of the cost. And so what we can do is still do BFS, but do not stop at destination. So usually when we do the BFS with n-weighted graph, as soon as we reach the destination, we immediately know that we found the minimum or the shortest path. But here the shortest path, we can reach it, but it can be a bigger price, like 500. If the direct path has bigger cost, then we still need to continue to find a better path, right? So we do not stop at a destination. So basically when we reach destination, just update the min price to get to it, right? Because that means we got to it, and continue, right? So this is what we are going to do. And then otherwise we need to also apply the other constraint, which is that K within K stops. So which means when we reach K stops, stop exploring neighbors, right? Because if we keep exploring neighbors, we will only keep getting K+1 and K+2 and bigger stops that are not valid, right? And then that's pretty much it. And then at the end, we can just initialize here. The first step, initialize min price to infinity. So the general gist is do normal BFS, like adding to the queue the source and going and popping each time and going through the neighbors and adding to the queue, right? But with some additional stuff, which is initialize the min price to infinity, and every time we reach destination, we update min price with the price that we reached with in the destination with at that moment. And then when we reach case stops, we need to stop exploring. And also another thing is that in BFSQ, put node, right? And then put this pair, basically put this triplet node, how many stops we did to get there, right? And then the cost so far, right? Because we will need to know the stops so that we will need the stops so that we can know when, if we reach case stops and stop exploring, we need to know the cost so that we can update the min price or the min cost. And then we need to also know the node so that we can explore the neighbors, right? So this would be our node that we put in BFSQ. Because usually with BFS we just put node, but sometimes we have to put more information. And then at the end, if min cost is still infinity, that means there is no path, right? Because if there was, we would have updated it here. So return -1, which is I think what the problem asks us to do, right? So yeah, if there is no such route, I would put -1. And also for another thing here is if a neighbor, while exploring neighbors, if a neighbor if going to that neighbor has cost bigger than the current min cost, that means it doesn't make sense to go there, right? Because if we go there, we will incur that cost, and from there we go to more neighbors, or more like explore the path more to get to the destination. We'll only have bigger cost, and so we will not update the min cost because of this neighbor, so there is no need to explore it, right? It doesn't make sense to explore it. And so this is to reduce the number of steps for us and to have to have less time, to do less runtime, to have less runtime for this algorithm, right? And those pretty much, I think, all we need. That's pretty much all we need. And then let's see how much time will this take. So first we will need also to, before BFS, we will need to construct the graph, because currently the graph that we are given is in a format that is not really amenable to just saying what are the neighbors of 0. With this, we can't really say it directly, so we need to construct a map, the graph like a map of nodes to their adjacent nodes. Because here with this format we can't really easily do that, so we will need to do that with this one. And this would be just the O of E, which it's just the length of this list, right? The length of the number of edges that we are given here. So it's just O of E. Now for our BFS, we would do so BFS usually the runtime is just O of V plus E, because at most we so V for the nodes that we will adding the node that we will add to the queue, at most V node, like the number of vertices that we will add to the queue. And then because we are exploring each set of neighbors, that's E. And so this is just the normal time complexity of BFS. And so overall, our time complexity would be O of V plus E, so 2E, which is just O of V plus E. And that's, what is V? V is N, and the E is the length of edges, right? That we have here in the input. So the number of, it's given as flights, right? So the length of flights, or the number of flights. So let's just call m number of flights, and so that would be m. That's our time complexity. For our space complexity, that's just the queue that we will use, which will contain at most OV, the number of vertices, which is just all that. So that's pretty much it. Now let's code our BFS here with keeping in mind the observations that we made here, or the implementation detail points that we listed here. So let's do that. So first we need to construct the graph, right? So step 1, this is 1, and then 2, we need to do BFS. So we need to construct the graph here. So our graph would need to be just the collections of default dict that gets initialized to list, so that those that have empty, that are the nodes that didn't have any flights, can just be initialized to an empty list, and so that when we're exploring the neighbors, we will do nothing basically. And then we need to go through the flights and add them. So that would mean, so the flight is source, destination, and then which is u, v, and then the cost, which is w. So let's just call it in flights. And so we would add, say, graph of u. So it's the directed graph is equal to vw. vc actually, right? And we need to start our BFS, and so that would mean we will need to have a queue that is a collections.dq, and we need to put the first the source, which is s, we said node, stops, and cost so far. So stops is just 0, and the cost so far to get to source, that's nothing because we start at source. Let me just call this one s and this one d. And so that's pretty much it for that. Now we will do our BFS, and we need to get the first element of the queue, and so this will give us node, stops, then costs. That's what we put in our queue. And then we will need to do the things that we said here. So we put this, we need to initialize min cost to infinity, and so we need to have min cost that is equal to float, right? And then we will need to not, when we reach dest, just update the min cost and do not stop and continue. That's what we said, because with BFS, so we are not sure that, because it's a weighted graph, a BFS, we are not sure that we reached the minimum cost yet, because we might be able to go another level and achieve a better cost, because the two levels had a smaller cost, right? Than that level that we went through, then the edge of that, like shorter number of levels that we went through before, right? And so we can do if node equal to destination, then we just update the min cost, right? So that would mean min cost, and this current cost is, this cost is just the cost here plus so it's just cost actually, right? So if this is the destination, then just we update the min cost that we found so far with this new cost, right, to get to d, right? So this would be the accumulation of cost, which we said here is cost so far. So let's just call it cost so far so that we don't get confused. And we said another thing is when we reach case stops, we need to stop exploring, right? So if stops is when we exceeds actually case stops. So if stops is bigger than k, or if the price of that neighbor will certainly be bigger than the neighbors will certainly be bigger than the min cost, and that we can find that is if the cost so far is bigger than the min cost, that means there is no need to continue, right? The neighbors will all have something bigger than min cost, and so we'll not achieve something bigger, so it doesn't make sense to go there, and so we need to continue. I forgot also to put here continue, because if we reach the destination, there is no need to go to other neighbors, right, of that destination node. We are not interested in that, right? We want to explore the rest of the queue to see if that can give us a better cost, right? And now we can go to the neighbors, and so the neighbors would be neighbor, right? And then we would have neighbor stop, let's call them, and then we would have so we would have this from the graph. So we'd have neighbor and neighbor cost, or let's call it just NC, in the graph of node that we just, so that's pretty much it. And now we will need to add it to the queue, so append, and we need to append the node, the stops so far, which is the stops to get to node plus 1, and the cost so far, which is the cost to get to node and the cost to get to the neighbor, which is NC, right? And then at the end we return min cost if min cost is different than float infinity, right? Otherwise, which means it was equal, we just do this, right? If it's still infinity, we need to return -1. And that's pretty much it. Float. Yeah, so it's a list of neighbors. So append it's cost so far actually. So okay, so that seems right. Let's try the second example. And we want to go from 0 to 2 with 0 stubs. Okay, so that passes. Let's submit. Okay, so that passes. Now, one other thing we can think of is that this problem here, if we look at it, it's just what do we have here? It's we have a weighted graph, right? A weighted directed graph with no negative cycles. We don't have any negative weight edges, right? And we don't have any so basically the problem says that there were no duplicate flights and no self cycles, so we don't have negative so the flight cost is always also positive, right? Will be in this range, so it's always positive, and so our graph has this property. And finding the minimum path, and so this is our graph type, and finding the minimum cost or the minimum path, min path, like in terms of weights, in terms of edges weights, is for a graph like this, there is an algorithm that already does that. That's exactly what Dijkstra's algorithm is designed for, right? And so instead of doing our custom BFS that we did here, we can even make it faster with Dijkstra's algorithm. You could look up Dijkstra's some lectures on Dijkstra's or some videos or also Wikipedia, but this is what Dijkstra's algorithm does. And so let's try to write it up. So one thing we still need is our graph, and the Dijkstra is what we need is a priority queue to make. So basically, if we look at our BFS, what Dijkstra will do is that it is designed in a way so that we get the minimum cost out of the queue first, and so we use a priority queue for that. And by doing that, we guarantee that when we reach the destination, we guarantee that priority queue to pop the lowest cost first, so that when we reach destination, we are guaranteed that the cost is the best we can do, right? So you can essentially think of it as BFS. BFS does the same thing for unweighted graph, right? Because BFS for unweighted graph, when we reach the destination, we just return that level, because that means that that's the best we can do. And the same thing for Dijkstra, it just does that differently. It uses the priority queue to pop the lowest cost first, so that when we reach the destination, we don't need to keep going and keep updating the mean cost. We just can return the cost that we found right away, because we know that that's the best we can do. And so it can saves us a lot of time by using just this extra space for the priority queue, which essentially is also we are already using a queue anyway. And so that's how it's faster, right? And so let's see how can we code it up. And so first, also the complexity of Dijkstra's here is that we need to construct the graph the same way we did before. So that's O of E, which is O of M, when we said that M is the number of flights. So construct a graph is construct graph. That's the so that's that. And then the Dijkstra's algorithm itself, that uses we need so with the size of our priority queue would be at most v, like at most v nodes. We will put at most the number of nodes in that queue. We don't put nodes that we put before, and so we know that it's O of v because we put those v times, and then the priority queue to pop from it, that takes log of v, right? So popping from priority queue is log of v. And so since we do that for each iteration, we have v log of v. And then for every edge that we push for the neighbors, so this is one thing we do in the iteration, is so we pop and then we push the neighbors. We push neighbors, right? And the push operation on priority queue is also log of whatever we are pushing, and we push the number of edges because we are exploring the neighbors, so it's log of e, right? And since we do it also the number of edges times because of the number of neighbors, and so it's the number of neighbors, so pushing neighbors would be the number of edges or the number of neighbors, that's e log of e. And so we have the popping operation for all of them is O of log v, plus the push operations that we will be doing, which are O of e log e. And so overall the entire thing would be O of e plus v sorry, here I said one push operation is log of v because the queue will contain at most v nodes. That's what we said here, at most v nodes. And so it's the number of pushes that we will do though are e because of the number of edges, and so it's O of e log v. And so overall it's like O of e plus v log v. And so it's, for our case here, it's around O of the number of edges, which is m, plus n log of m, the number of vertices, which is n. So it's like this. So you can see it's a lot better than our original implementation. And so now we can do our priority queue, which would be just a heap. And in Python, a heap initialization is just this, but in order to push, we'll use heap queue. So let's import that. So we need to use import heap queue to use a priority queue in Python, and we will use its heap push and heap pop. And then we will need to add to our priority queue we'll need to add the source one. And so to do that, we'll do heap push, and to priority queue we will add source. In the same way, we will need to add the stops, and then the cost so far, which would be 0 also, right? And now we will need to do, while we have elements there, we will need to pop from the heap, and that would give us node stops and cost so far, the same way we did with BFS. And then we'll check if we reach the destination. Now this is the difference with BFS, is that if we reach the destination, that means we are done. That's the best we can do, and so we can just return the cost so far. There is no need to keep going. Now also we need to check if, to do the condition that we said earlier with BFS, is that if the stops are more than k, then that means we are done, and so we should return, we should continue. Otherwise, we don't need to explore the neighbors after this k stops, because certainly we won't find anything good. And then we are going to traverse the neighbors, and so those would be neighbor and neighbor cost in graph of node, and we are going to need to push these. And so we need to push the neighbor and the number of stops and the cost, which is cost so far, plus the new cost of going to that neighbor. And at the end, if we didn't find the destination, we can just right away return -1. There is no need to keep track of any min value, right? And that's pretty much it. It's a lot shorter too. Heap queue. It's not heap queue pop, it's heap pop. Yeah. We need to pass what are we popping from, so it's the priority queue. Okay, so it passes for that one. Now let's try for this one. And this one is 0, 2, but we have k stops. We have 1 stop we can do. This one doesn't work. Okay, let me make sure I did put, so we have 3, we go from 0 to 2, and the stops are 1. Okay, so there is something we are doing wrong here. I think it's maybe, yeah, no. Okay, let's see. Yep, so the problem is that priority queue, we want to pop the lowest cost first, and priority queue in Python uses the first element as the key. And since I'm putting the node, so it would use the node's ID or the node's number and pop the nodes with the lowest number first, but that's not what we want. We want the lowest cost first. So we'll need to put the cost first. And so let's change our node structure here to be the price so far, the number of stops so far, and the node. And so it would be the cost so far, the number of nodes, the number of stops, and then the node, so that the heap queue can prioritize by the cost so far and then by the number of stops after that if they have the same cost. And so here when we are adding them, we will need to add it in this order. Okay, so that passes. Now it's working correctly, and let's add. And we need 0 stops Yeah, so I forgot this. Okay, so that looks good. Let's submit. Okay, so that passes. So we solved this with Dijkstra, and we solve it with BFS. There are also two other solutions. One is kind of DFS, but more like backtracking, where we can just do normal DFS with a visited set so that we don't visit something multiple times. And whenever we start visiting a node, we add it to the visited set. And when we are done exploring all the nodes, we remove it from the visited set. But the most important idea with that DFS solution is that if we find a cast that where we can't reach a better cast from there, we can just stop our DFS and do pruning of that DFS path. That's one way to solve it. DFS is a little bit not very intuitive to apply to shortest path type problems, so maybe we should avoid it. But there is also this problem also can be solved with Bellman-Ford. But yeah, I'm not going to explain it here, but you can look it up if you are interested. Yeah, that's it for now. See you next time. Bye.